And this is like really, and out of his control, some family stuff. And so, really, we've now lost Andrew. So Jimmy, we lost earlier, that was something else. But I've never had this happen, ever had this happen. And so, and not in the same class, in the same semester or anything else. So this is really, really interesting, happened in the middle of grading. That's why I didn't get the grades up until this morning. Let's start where Chris is the only one left, that he had to do all the grading. And so anyway, I got the grades up, you have them. We're frantically trying to find other people, but then that's cut into everything, the tutoring hours that they're available, whether or not we have somebody sitting in the class that can answer questions. We don't have any of that right now. So we're working on it. It's the wrong time this semester to try to get people because nobody wants to start in the middle of the semester on a job. So we're working on it. We're working on it. But I'm going to have to shift Chris over, and he's going to have to do some other tutoring hours during the week, and I'll try to get that posted on Blackboard. And then I have office hours, and Dr. Zhao has office hours, and we can, hopefully get questions answered. Yeah.
So if you're looking to go over your exam and look over it, how is that going to work? Do we have to wait for Chris? Are you going to have some updated office hours too, or today?
You can come by during my office hours or make an appointment with me to see it, or I'm going to have Chris available as well. So, but I just haven't gotten to talk to Chris yet today. He was frantically trying to grade all of your exams. So, yeah, he's going to have a little bit of time available on Tuesdays and Thursdays. So, yeah. It's weird, but we're really, really, really trying right now to get somebody else to step in. Well, actually, we need 2 more people at this point, which is amazing. But anyway, what we're moving into today is Chapter 5, and today will be transportation models, and then on Thursday will be assignment models. And what you'll notice about them is that they follow the same structure. I mean, they're just exactly the same in the structure. There's actually 2 different ways you can do it, as a matrix or as a list, but the structure will be the same. It's just the context of the problem and what you're trying to accomplish is different. For instance, what you're trying to accomplish with the transportation model is that you're typically trying to get things from a source location to a destination location. And when I say it's not just one, like you have multiple source locations, multiple destination locations, and you're trying to figure out the best way to ship from here to there. Okay? And typically it's because what you're trying to do is to do this in the most cost-effective way. So normally what you will see with transportation problems is that you're trying to minimize the cost of shipping from these locations to these locations. Okay. When you actually get into the model, you're going to say, oh my gosh, this is the simplest model we've ever solved. Because it is, on one hand, we'll look at it in different ways and we'll make modifications and all kinds of other stuff, but the original model, you'll just be like, yeah, it's pretty straightforward. Okay. We have one problem that we'll be working with and just doing it in a lot of different ways and answering a lot of different questions afterwards. But what we have is companies trying to get things from their plants to their distribution centers. And so you have the capacity at the plant, you have the demand requirement at the distribution center, and you have the costs associated with how much it costs to get from this particular plant to this particular distribution center. Okay, so every one of those costs you would have as well. In fact, those are your 3, they used to have this in your book, I don't think they have it in there anymore, so that's why I have it on here. Those are your input variables. You know these things. These are the given pieces of information that you have: the plant capacities, the distribution center demands, and the unit shipping costs along any of those paths. Okay. And then what we're asking Excel to do is tell us how many units to ship from here to there. You know, what configuration. You know, which ones to ship from, how many to ship. With our overall objective in the problem is to minimize costs. I mean, that's the idea, is that we want to do this in the most cost-effective way. We have to calculate some things. We have to calculate how much is sent out of each plant, and we have to calculate how much is sent into each distribution center. And the reason we have to do that is because we have to constrain those. We calculate things typically because we're constraining them, okay? Or they're our objective. or whatever, but we have to make sure we don't send more than the capacity at the plant. We have to make sure that every distribution center gets what they needed, okay, gets at least what they needed. These are our 5 plants and our 9 distribution centers. Those numbers are going to be on the worksheet when you see it. So those are the capacities, those are the demand requirements. And the one on the worksheet looks better than this, but associated with every path, in other words, if you send from plant A to DC1, it's gonna cost $180 a unit. From plant A to DC2 would be $215 a unit. So for every one of these, you see a cost associated with it, except right here, where you see these NAs, where those are what we would refer to as disallowed paths. Plant E can't send to distribution centers 7, 8, or 9. Okay, it's just, they're disallowed paths, or paths that can't be taken. So there's an NA there. We'll have to deal with that later. Another way that you could represent this would be in the network model style, where you would have these, the circles on either side, which we refer to them as nodes, but you'd have plant A and its accompanying capacity written there, and then the distribution centers on this side with their demand requirement written there. And then along the path, you'd be seeing the cost of taking that. It would be a lot messier looking than this though, because these first 4 would all have 9 arrows coming out of them. They'd be crisscrossing each other. The last one, of course, would only have 6 arrows coming out of it because it can't do 3 of those paths. But that's one way you could represent it. I think most of us, visually it's just easy to see on the spreadsheet as well. This is another way to look at it. There's some terminology, some of which we'll use, not all of it. Those circles at either end are the nodes, and then the arrow is, they refer to as the arc. That's that path. There is one that we'll use more, I guess, and that's the decision variables are actually the flow. So the decision variables are how much we determine, not we, because it's Excel solver that determines it, but how much is determined that we send from here to there kind of thing. And so that's what we refer to as the flow. The arc capacities are basically just the capacities, the plant capacities for us in this problem. Okay. So we're gonna solve it, and like I said, you're gonna say, oh my gosh, this was the easiest, quickest solver we've ever gotten to. Okay, and we'll have an optimal shipping plan, we'll talk about that. But then we're gonna do some other things with it. We're gonna look at it in different styles. We're going to come back and answer all these different questions, do some solver table, do some model modification. So we'll come back to that. That'll be like the last thing we do after we're done with it. Well, not the last thing, it's a lot of what we do, but then we have to get done with the model first. Okay. So here's how you see it in a style called the matrix form. What you see is a table that gives you every combination of the 5 plants, 9 distribution centers, and what their costs are. Of course, with this particular one, you also have some NAs over here. Okay? You have some that you can't follow that path with. Then you see an identical matrix right below it that's all light red. So you know what that means. You know those are the changing cells. Those are the ones that Excel's going to be filling in. Okay, that's what it's going to be doing. So Excel's going to tell you, plant A, send this many to distribution center 1, 2, 3. I mean, some of them it'll say don't send from that distribution center. You may just send here, and here, and here, and here. But eventually, it's going to fill that in. We have to make sure that what gets shipped out of any given plant doesn't exceed the capacity that they have at that plant. Okay, and then we have to make sure that what gets shipped to a distribution center meets their demand requirement. All of this overall objective is that we want to do this in the most cost-effective way. We want to minimize this overall cost. Okay. So you're probably looking at it already and thinking, yeah, it does look like it's going to be pretty straightforward as far as filling in the model. Because what do we do here in cell K12 to figure out how many were sent out of plant A? What would we do?
Sum all those up.
Yeah, you just sum that row, because basically whatever it tells you to send from plant A to 1, 2, 3, 4, up to 9, whatever that is, in total, that can't exceed what the plant has. Okay, so you sum that up, you do the same thing for the others, because you can't let that exceed the capacity of that plant. You can't ship more than they have there. Same idea here. You've got to make sure that everything that gets sent to DC1, regardless of where it comes from, meets in total, meets their demand. So what do you do in cell B17? Yeah, you just sum up that column. And again, that would be true all the way across here. So those are important calculations to make, because those are our two major constraints in this problem. And then, last but not least, the objective cell, when you're trying to come up with total cost, what are you gonna do to get total cost? Yeah, and it's the sum product. I'm not typing, my hands are frozen in this room. It's the sum product of what? Right, the whole cost matrix, okay, and the whole changing cell matrix. Because what you have, now I think a lot of times up to this point when we were doing some products, we were always, for the most part, we've used vectors. They've either been just columns or just rows, and we knew that the shape and the size had to match. But I mentioned, or maybe we've had one before where we did two-dimensional, but as long as the size and shape of those two ranges match, then you're fine. Because it's gonna take every one of these and say, I don't know how many it's gonna say, but whatever it tells you to send from plant A to DC1, for each one of those, it'll be $180. Add that to all of these times 215. Add that to all of these times 65. I mean, so it's, and obviously some of these are gonna be zero, but when they're zero, there's no cost associated with that when you're multiplying by zero. So that's what's going to give us our overall total cost. And that's gonna be our objective function. Okay? That's gonna be what we're trying to minimize. And you're done with the model. See, I told you would say, oh my gosh, this is the smallest, quickest, easiest model we've ever done. We need to go into Solver to set it up. And again, our objective is to do what? Minimize our total cost. So total cost is down there in B21, we want to minimize that. So that's the whole goal, is that we want to minimize total cost. By changing, well, all of these, because this is what we're trying to get Excel to fill in, is how much to send from this from this source to this destination. Okay, so B12 to J16. And then we have constraints. What's one of our constraints? Yeah, the total shipped, total received, whichever one we want to do first. Make sure that the total shipped, which is right there in K12 to 16, does not exceed or is less than or equal to what you see in M12 to M16, because we cannot send more than the plant has. So that's a pretty straightforward why we do that one. Yes.
Integer constraint?
And we are actually not going to do the integer constraint on this one. Yeah, it's not necessary, and there's one part that will mess us up on if we have it in there, so we'll just leave it without it. Yeah. The other one of those constraints they're the two big constraints, but is that we make sure that the total that's received by the distribution center, that would be in B to J17, that's greater than or equal to B to J19. So just on this one for a second, when you're looking at it, you might wonder why are we trying to send them, greater than possibly what they ordered. We sort of get in the habit of doing that a lot when it's really not necessary. We could put an equal here, and I really wouldn't care one way or the other if it said equal or if it said greater than or equal to. We occasionally have problems like that simulation problem where we're buying up toys, and the way those parts come in batches, it was necessary to buy more parts of some of them than you needed, and you had to do that. So setting it equal, would have been a bad idea in that particular problem. It wouldn't be a problem in this one. We could do it. It wouldn't be an issue. We kind of get in the habit a lot of times of doing that greater than or equal to just because of those types of problems, because we know full well that this is not going to suggest we send more product to them than they asked for. because it's a cost minimization problem. So it's not ever gonna say, I'm trying to minimize costs, so I'm gonna send you more than you wanted. I mean, nothing about that would make sense. So we can put the greater than or equal in there and just not, and we're not worried about it. We're not worried about it. We don't feel like we have to, force it to be an equal, because it's not gonna happen. It's not gonna happen that it's gonna send more, unless for some reason, like I said, it had some kind of batching way that you were getting stuff that it would be necessary, and then you'd have to have it in there anyway. So, okay, those are your two constraints. That's it. Okay, so it's still a simple problem. I mean, really, if you think about it, you're minimizing the total cost by changing these changing cells, and then subject to just your two main constraints. Don't send more than you have in a plant. Make sure your distribution center gets all that they need. And you solve it, and it solves nicely. But when you look at this solution, what do you see that might bother you a little bit?
All the zeros.
No, it's okay for it to have a lot of zeros. That actually isn't a problem.
When I see you're shipping some to DC8, DC9.
Right, so here we were with disallowed paths where we said Plan E cannot send to distribution center 7, 8, or 9, but it sent to all that it had to those two distribution centers 8 and 9. Why to do that? In the model, why to do that mathematically?
Told.
Well, those were free. I mean, to Excel, that's zero value, okay? So when you multiply by that, those were the cheapest paths it could possibly take, were the ones that were free, yeah. So we didn't do anything to prevent that from happening. And there's 3 different things that you can do. One of which I think your book suggests, and I don't like very well, and 2 that I think, well, 2 that work, okay, and are right. One of them is okay, and this is how your book would suggest to handle this problem, is go into these that are NAs and put, an artificially large number in here. Okay, we don't probably have to go that high. I could have just gone to 1,000, it probably would have handled it. But go in and put some huge number in those disallowed paths, okay? I can see that. I go back now after I have it, you can put 1,000 in there and it'll work, because that's so much higher even than the other numbers. You can go in and solve that again with those really high numbers in there, and now you get a valid solution. See, because your last solution was not an okay solution. It was using paths that you weren't supposed to be using, okay? Now you get a perfectly okay solution. It avoids these. Of course it avoids these. I mean, they're crazy high. So it avoids these. This is a valid shipping plan that you could use, and the cost is, I don't know, 100,000 more than it was before, more than that, 140,000 more than it was before. Okay, of course, okay, because you're not using things you weren't supposed to be using. Okay. Here's the problem with that. You don't have this, I don't think, but I've got this little bitty example over here, which is essentially the same kind of thing. 3 plants, 3 distribution centers. There's the capacity, there's the demand. Everything's set up just like I just set this last one up, right? These 2 right here are actually disallowed paths. I'll just kind of do something different with them so you can see them. Yeah.
So like on the test, like if we have like a matrix problem, for example, and we use solver and it comes NA, would you like ask us, oh, put this value?
Well, that's what we're doing right now.
Oh,
okay, so that's what we're doing. So hold that thought. This is one of 3 methods that you could do to handle this, and this is the one that is even suggested by your book that I don't like as well, and here's why. Those 2 paths right there are actually disallowed paths, okay? So what do? We go in and we put a great big number in there. We put a number much bigger than all the other numbers. I go in to solve it. Okay. Everything's in here just like, minimize this by changing this, subject to your 2 constraints, just like you want it to be. Solve it. Okay, all is good. All is good. It did not use those 2 paths. Okay, So we're good, right? We currently have a capacity of 500 units. Our demand right now is only 450, okay? If DC2 decides they need 250 units instead of 200, that's not a problem. That's still within our 500, right? So we should be okay with that. So I changed that, the required amount that they want to 250, and I go back in to solve this. I have a cost of 25,000 right now. I go back in to solve this, I solve it, it's solved, okay, it's solved. My cost jumped $50,000 on those 50 units because look what it had to do. Okay. So DC2 had already taken all 100 that you had at plant 1, all 100 that you had at plant 3. If they're not allowed, the only thing left if you increase their demand was to take it from plant 2, which was supposed to be a disallowed path. They weren't supposed to be able to do that, okay? So when you put in the really large numbers, you deter it from using those paths, for sure. But if it has to use them, because it doesn't have any place else it can get them, it's still going to use them. You're just gonna get incredibly high costs associated with it. So it didn't stop it from using it, it just deterred it from using it. When it had to, it used it, okay? So in this situation, we shouldn't have gotten a solution to this problem. We should have gotten infeasible. It should have told us what we're trying to do is infeasible. We can't get 250 units here if they can't take from plant 2. Can't happen. So we should never have gotten a solution to this problem. We should have gotten an infeasible solution. And so that's why I'm not big on this as the way that you choose to solve the problem, because it's really not preventing what you wanted it to prevent. It doesn't necessarily end up with infeasibles when it should have. So I got 2 other ways that you can do this, and I think both of them, are fine. Okay, so if this was back to, just being NA, okay, if this was just back to being NAs, then this is one of the things that you could do. You could have gone into the solver and just, left it all as it was, but then added a constraint that these things had to be 0, okay? So just force them to be 0. Don't let them use it. And so you just go back in and you add a constraint and you say, these cells right here have to be equal to 0. Go ahead and hard code a value in here. But anyway, make sure that those things are 0. So now you just added an extra constraint with those NAs being 0. Okay? So that now when you solve it, now remember the NAs are back in there. When we had the NAs in there before, it used that. It used those 2 paths. But now you're preventing it from using those 2 paths. And so you get the right answer, and it puts zeros in there, and it doesn't use it, and all is good, right? So that's one way that you can handle it. Okay, so that's one way. Another way that you could have handled it would have been, and I'm going to take that 0 constraint out. I'm going to delete that 0 constraint back out, put it back to where it was here. Would have basically just been to recognize that those were never changing cells to begin with. Okay, I'm going to go ahead and shade them differently so I know. They really aren't changing cells, are they? There aren't ones we should have been using because they're not paths that we could use. The only place we want Excel putting numbers is into these light red cells, not into those 3 cells. So a different way to do it in Solver, instead of adding a constraint like we did in the last one, would have been to just change the changing cell area to reflect that those aren't changing cells, okay? And so just put the changing cells in, however it works for you to put them in. You can do, however you want. It obviously has to be done kind of in 2 different ranges, but recognize that all these red cells are your changing cells, but not those 3, instead of the extra constraint. Okay. Again, you click solve, and you get the right solution, and everything's good. Those aren't changing cells. You don't even get zeros in there. You don't get anything in there because they weren't changing cells. Okay? And both of those methods are fine. Okay. I don't like the one where you put a really high value in there, but I actually think your books will suggest that. And I don't think that it's the best solution when you could do these. However, this example is really easy to do. Either one of the two solutions I do like, okay, are easy to do in this example, and here's why. Because your changing cells are clustered all your NA cells are clustered all together. It made it where it only required one additional constraint if you chose that one, or it was pretty easy just to select around them, okay, because they're right clustered there together, and so it's not a problem. So you won't see it in this example, but the very first example that we do on Thursday, which is an assignment problem, but assignment problems are structured the same way, is gonna have disallowed paths like here, and here, and here, and here, and there, and there, and there, and there. You know, just scattered disallowed paths all over the place. Begin to make you want to use the really large number thing, okay? Because it's harder to work with it. If you're adding the constraint of making those cells 0, you can't, in that constraint box, you can't select multiple cells and then say make them equal to 0. You have to say this one's equal to 0, that one's equal to 0, this one's equal to 0, that one's equal to 0, this one's, you have to do a whole bunch of constraints in, setting them all equal to 0, hoping you don't forget one of them, okay? Or, if you do the thing where you select around them, it's tedious. It's tedious, you know, you select these, and then these, and then those three, and then these, and then, you know, and you're selecting all around. So both methods are more tedious, no doubt about it. They're more tedious to do when you have a matrix and it's very big and you have a whole bunch of scattered but disallowed paths in that matrix, okay? Which leads us to another solution structure, okay, that works better in those instances. And that's to set this whole thing up as a list and not a matrix. Okay? So you have to have all the same information, you have to constrain it in all the same ways. You just set it up differently. And the way that you set it up here is that you still make sure that you get every combination. You know, because in our matrix, we got every combination of plant to distribution center, right? Well, you still have to have that. You still have to have every combination of plant 1 to the 9 distribution centers, plant 2 to the 9 distribution centers, plant 3, this goes all the way down, okay? You still have to have every combination because they all have a cost associated with them, okay? Just like the upper matrix in the matrix solution, the upper two-dimensional array, they still have a cost. There's still a cost associated with all those, okay? And we will still be asking Excel to tell us how much to ship on each of those, okay? So now what used to be two little two-dimensional arrays is now in list form. And here's what it does for you. If you had scattered disallowed paths, you wouldn't put them in here. You would just, if you can't go from 1 to 7, that wouldn't be there, okay? If you couldn't go from 2 to 8, that wouldn't be there, okay? You would just not put them in the list. See, that's not possible to take one of those out of here. Okay, with the nature of the two-dimensional, you can't say, oh, well, I'm just gonna take this one, that one. I mean, it's not possible to do that. But it is possible to do that in a list because you just take the row out, okay? It's just not there, which I know for us is just these down here, again, but this was an easy one to do the other way. These wouldn't be there. They wouldn't be there. They'd just not be a part of it, just like any that were up there that couldn't be used wouldn't be there. So we're gonna pretend those aren't there. Okay. So you have everything that you need. You have the cost information. You have a place for Excel to assign what the flow will be. But you have to do the exact same two constraints that you had to do in the other problem. You have to make sure that what you send out of the plant doesn't exceed its capacity, that what you send to the distribution center meets their demand. You still have to do those two things. That has to be done. Okay, this is where it's not as simple as the matrix, but this isn't hard. And then, of course, your total cost is actually the same. You still are taking the total cost and minimizing it. One of the things that will make what we're about to do here in these two constraints easier is if these columns are named. It really makes it easier. So I'm going to go in and name A5 all the way down to A46. These aren't here. Pretend these aren't here, yeah. Okay, so from A5 to A46, I'm gonna name that plant. I'm gonna turn around and do B5 to 46. And I'm gonna name it just DC. I'm gonna do C5 to C46. I'm actually gonna name that cost. And then D5 to D46. I'm gonna name flow. You don't have to do this, but in what we're about to set up in the constraints, it's so much easier if these columns are named. It just is, so it's a good idea. All right. So again, I have to have a constraint that says what I send out of plant, and and I never fix this year after year. Somehow my plants became 1, 2, 3, 4, 5 instead of A, B, C, D, E. I don't know when that happened, but it happened. I think I was doing it really fast, and so it was easier to number than it was to do the letters, so I have no idea. Doesn't matter, we have 5 plants. What gets sent out of plant 1/A, okay, can't exceed 1,500. So we still have to sum up what comes out of plant 1, right? Because it has to be constrained by the 1,500 capacity. Okay. And that's this right here. Okay. And then we'll have to sum out of what comes out of plant 2, right? That's gonna be this right here. That's plant 2. Okay. I don't wanna type this 5 different times. I don't want to have to, set it up kind of manually in that way, because that's not as easy. It was a lot easier when it was in the matrix, I just copy row to row.
This is a question, but like, what happens if you like highlighted, I accidentally highlighted from like D5 to D49 and I named it plant, but like now I'm trying to get rid of that and do it to 46.
Okay. You need to go into formulas, name manager, and then you'll find that, and you can either edit it right there and turn it into 46, or you can delete it and start over again, either one. Yeah.
Oh, okay. All right. Thank you.
So formulas, name manager. Okay. What can I do, I don't have to type this 5 times. What can I do to get the sum of the ones that are coming out of plant 1? What function could I use?
Sum it.
Yeah, because if I use a sum if, then it's set up and ready to go for all of them. And I'm summing it, remember how sum if works. What range am I looking at to match a criteria? Then what am I summing? Okay, so what's the criteria I'm trying to match? What range am I looking at? What criteria am I trying to match?
Where?
Yeah, I'm trying to look at the range called plant, and I'm looking for, at least on this first line, I'm looking for what?
6.
Yeah, I'm looking for plant 1. Well, I'm not gonna put a 1 in there because then I've hard-coded a number in there. I don't wanna do that, so I'm gonna reference the cell that has that. And if these had been A's and that had been an A, it worked just fine. It didn't have to be a number. Like I said, I don't know why I did that at some point, but I did. And then what am I summing?
Cost.
Not the cost. I'm summing the flow. This is just like I did in the red matrix on the matrix one. I summed that row. Well, here I'm summing anything in here that is plant 1, okay, that goes with plant 1. Now, the nice thing about having named this is that now I don't have to think about where absolute references and all of that, and dollar signs and all that stuff. It is easier just to follow it, just follow the logic of it, but it also, plant and flow are now absolute references to those ranges, and I don't have to, mess with dollar signs at this point. So, copy that the rest of the way down. And each one of these, of course, is looking here to match that to sum this. I have to bring hand warmers to class. to sum up all that is going to a distribution center so that I meet their demand, right? But it's a little bit different now because like, what's going into DC1? That is, and that is, and that is. But again, I don't have to put this in manually because I'm gonna use what function? The SUMIF again. This time though, the range that I'm looking at to match the criteria is what? The DC. And of course, still referencing a cell that has 1 in it, so that it would be 2, 3, 4. And I'm summing 1. And it's still flow that I'm summing. Because if you remember, when it was in a two-dimensional array, you summed it 2 ways. You summed its rows, then you summed its columns, okay? Well, that's what you're doing here. You're summing it based on plant, and then you're summing it based on distribution center, okay? So you're doing the same thing. You're summing it in 2 ways. The relative and absolute is all taken care of. Copy it. Good. And then the total cost is just what? It is the sum product still. And it's just like it was before. Last time it was the sum product of the blue and the red, right? This time it's the sum product of the blue and the red. They just happen to be in a list instead of two-dimensional. And this time it's actually easier because we've named them. So it's cost and flow. But it's the same thing. It's the sum product of the costs and the flow. And that's what it was, even in a matrix. It's just we had named them over there, but because they were, wasn't as necessary. Names are great. Range names are great. You just sometimes, when they're not so necessary, you just don't have a tendency not to think about it and do it. When they're more helpful to you, those are the times when you really want to use them, and this is one of those times. Now, of course, oh, okay. No, more to this. So let's go into solver. Our objective is still to minimize total cost. Okay. So we want to minimize, in this case, G24. By changing, the red cells, which we have now named, so we can say flow, so that's a little easier. And we add the 2 main constraints, which is make sure you don't exceed your capacity. So make sure that G6 to 10 is less than or equal to I6 to 10. Don't exceed your capacity. And your other one, the inflow to the distribution center meets their demand. G14 to 22 greater than or equal to I14 to 22. So you same constraints, the capacity and the demand constraints you still have. Here's the difference. We don't have to do anything special to take care of disallowed paths, like setting them to 0 or making them not there, because they're not there. They're not there. The list can be set up in such a way that if you clean it up before you ever do the rest of it, if you clean it up and take out all the disallowed paths first, done. Disallowed paths aren't there. So there isn't going to be a problem with this. We don't have to do anything to it, and we can just solve it. And of course, we better get the exact same solution that we got over in the other one. You can bounce that off back and forth to make sure, but there's nothing different about doing it this way. There's a little work in making sure that this doesn't have the disallowed paths in it, and yes, it takes a little more thought to do the sum ifs, okay? If your problem is as simple as this one with the clustered disallowed paths, oh gosh, the matrix is easier probably hands down. I mean, you know, it just is, because it's so much easier to set it up. Sum's probably done, you know. It's so fast to do. But when you see the first one that we do in the assignment problem on Thursday, you're gonna say, okay, that's a good reason for a list. I mean, it really is. And so we'll get to do it in the tedious way and the list both, but.
Will we be making a list, like, or?
That's a good question, and I was going to right at the end of the other class, and then I just kept talking longer, and we I got a little bit early, but not enough. So if I don't do it today, on Thursday, and it'll probably be Thursday because that's when I'm doing the other class, I'll kind of show you how to set these up. And here's why. Of all the problems you do, these are one of the most consistent ones you will ever, they have a consistent pattern to them. It's like, this is what it looks like. You know 3 things. Well, okay, we'll do the transportation problem. You know 3 things: demand, supply, which is your capacity, and costs. Boom. That's it. I mean, you can create the whole thing if you wanted to. Well, I wouldn't make you type all of it in, but I'll show you how you can take things from one form to the other, or how you can just finish out a model. Okay. Because these are, you know, this isn't like the aggregate problem. I would never ask you to do it. You know, they're like, you know, they go from here to next week. These have just a pattern. They have an exact pattern to them, so they're easy to know what to do. So hold that thought. So either the end of class today if we have time, or later. Okay, so that kind of gets us through both matrix and list and understanding what they both look like, why we would set one up versus the other, how you handle solving it, you know, what you have to do, disallowed paths and everything. But as far as like going back to the last slide of the PowerPoint where all the questions are, the first one of course says, what's the optimal shipping plan? Well, this is the optimal shipping plan. You know, that's what we solved for. The plan is, out of plant A, send this to 3, 4, 5, and 6. Out of plant B, send everything you had to 7. You know, this is the plan. That's what you solved for, was the plan. Then it asks some kind of, first kind of open-ended sort of weird question. Why does plant D ship to DC2? DC2, right there. It does, it ships 255 units. When it's the highest cost of any of them to ship to DC2. So if you look at this, you do see that is the highest cost right there, but we use it, okay? So I guess then the question is, why? Why do we use that one? I mean, what would be some possible reasons? This doesn't have a definite answer, just kind of general, what do you think?
Because I guess with the other constraints, maybe because of capacity, in that role it was cheaper to go with that.
Yeah,
compared to the other.
exactly. So it still obviously did work out mathematically to be cheaper still to do that. D is a really high capacity plant. And maybe you have some cheaper places, but they don't have really high capacity, so the next thing you know, you've assigned your capacity to ones that were, like you said, less expensive, and so you went with that. Really, in the whole scheme of things, from the highest to the lowest cost at DC2 is only $55. From the highest to the lowest cost over here is $310. Okay, so there are some where there's a much bigger discrepancy and you want to go to the lowest, you know, cost one that you can, whereas here, yeah, you know, it just worked out like that. Like he said, it mathematically worked out that way. So there's not really other big answer to it than that. But then we move into some solver table questions. And here's the first one. How much are you willing to pay for additional capacity at plant B? Now it goes on to say, how much would you pay to increase that capacity? Okay, the PowerPoint has changed through time, so I'm just gonna do both of these because I don't even know what I have out there on the finished file. One of them used to say to 910, and the other PowerPoint would say by 910 units. Oh, it doesn't matter. The question will all get answered in the same way, either way we look at it. Okay, so that part doesn't matter. Let's go back to the first question. Remember, I always tell you in solver table, you say to yourself, what input am I varying, and what output do I need to look at to answer whatever the question is? Okay, you know, given the question, what input am I varying, what output am I looking at to determine the answer to that question? And so the question part of it is this: how much are you willing to pay for additional capacity at plant B? How much are you willing to pay for additional capacity at plant B? What's your input that you're going to be varying? The capacity at plant B. What's your output that will answer the question? The cost. Because what are you willing to pay? Up to how much money it saves you, in this case, because it's a minimization problem, how much money it saves you to have more capacity here. Okay. So I know that that's going to be my output cell, so I am going to name cell B21, I'm gonna name that, we can't say cost, because cost is on the other sheet, so I'll call it total cost, or total underscore cost, or something along those lines, total cost. Okay. Okay, so when I go into, I forgot, I turned this off in between classes. Wish it would just stay on. Okay, so when I go into solver table to run it, again, we just talked about what my input is that I'm changing is the capacity of plant B. So that's just a one-way table, that'll be the only